Great. Welcome to the next serve module, still part of week 1 if you're in 4.2.3, on plate tectonics. This is probably one of the most central theories in geology. And what we're going to see is that it's also a wonderful illustration of the scientific method, how the scientific method works, and how the scientific method does sometimes get things wrong, but when it gets things wrong, it has mechanisms within it that will correct those wrongs. So let's just quickly review the scientific method. And what we're going to be doing in this video is 1, laying the groundwork for your note-taking. 2, we're going to be introducing sort of one of the foundations, the sort of foundation for this. And then in the following videos, we'll look at some of the predecessors to plate tectonics and the evidence they used, building upon this script we have here. And then finally, looking at what actually laid the evidence for plate tectonics as we roughly understand it now. Short story, in a couple weeks, if you're in my class and I'm still doing it this way, you're going to be looking at some challenges to plate tectonics. So let's get the scientific method up here on the top of the screen. Okay, so we got the now 5 components of the scientific method up at the top of the screen. If you want to pause and jot those down in your notes, that's probably good. This chart's going to be a little bit wild, but hopefully with the video format, I can make it a little better than it's been in past lectures. So remember that observations, I also like to conclude with observations, previous work. And one of the foundations for previous work, a very well-documented phenomenon, is the theory of isostasy. So you may wonder why it is I'm putting isostasy theory in observations, even though it's a theory. The idea of isostasy is a beautiful one. So the principle of isostasy is that any object floating in a fluid will displace a mass of fluid equivalent to the mass of that object. So we're seeing and remember that first layering, we have the lithosphere, which is a solid, and the buoyancy of the lithosphere, the reason the lithosphere floats is because the crust is less dense than the mantle. And the fluid is kind of this middle mantle asthenosphere that's floating. It's a very thick fluid, and motions are very slow here, but every piece of solid ground you're stepping on is in some way, shape, or form floating on this liquid-like asthenosphere. And so the lithosphere is essentially displacing a volume of asthenosphere fluid, or if we want to think of it sort of a little bit more quick and dirty, all bits of crust, whether it be ocean crust or continental crust, are displacing a volume of mantle that has the same mass as the crust above it. But because the crust is quite a bit less dense than the mantle, the crust will top of the crust will rise higher than the surface of the mantle fluid if it were allowed to come up to the surface. We also know from our lab activity by this point that the ocean crust is quite a bit denser than the continental crust. So continental crust will on average float a little bit higher. We also know through the theory of isostasy that a thicker object, if it's less dense than the fluid is floating in, will have a higher upper surface than a thinner object. So mathematically, the crust has a density of about 2,700 kilograms per cubic meter, or 2.7 grams per centimeter. The ocean crust has a density of about 3,000 kilograms per cubic meter, or 3 grams per centimeter. And then, of course, ocean water has a density of about, I give it 1,000 kilograms per cubic meter. It's probably actually 1,030, but we're not going to worry about that 30 for this part of the lecture. And so we assume that the ocean thickness is about, and so we can do here is say that density 1 times thickness 1 will equal density 2 times thickness 2. In this case, Density 2 is the density of your mantle rock, the peridotite. And peridotite has a density of 3,300 kilograms per cubic meter, or thereabouts. So that if you have a 25-kilometer thick block of continental crust, the surface of that continental crust is going to be substantially end up being quite a bit light. Quite a bit lighter than your ocean water and ocean crust combination, and the surface of the continental crust will poke up above the surface. Now this leads to two interesting major observations. The first is that by about 1900, people had a pretty decent idea on a very large scale of what the surface of the ocean looked like, what the surface of the Earth looked like, and what the bottom of the ocean looked like. Now, they didn't know all the details. There's still details we don't know, but they had they had at least a rough map, and we'll get into that when I do geology of the sea floor. And what if you were to break up Earth into a bunch of 1 kilometer squares, and then arrange those 1 kilometer squares of Earth from the highest altitude, the highest mountains like Everest, to the deepest trench on the sea floor, this would be sort of the graph you'd get. You'd have a very few regions of the Earth that are very highly elevated. Then you'd have this broad region of Earth that's between about maybe 1.5 kilometers and above sea level and just a little bit below sea level. And then you'd have a very limited region between that was of sort of this intermediate depth. And then you'd have a vast area of the ocean floor that was between about 4 and 6 kilometers, and then a much smaller area of the decent floor. So what you're seeing is what's known as a bimodal distribution of Earth's surface. It turns out this is a relatively unique quality Earth. You don't see this on Venus or Mars. And what it implies is that different processes are responsible for creating the ocean floor, and the processes that give us the ocean floor are different than the processes that give us the continental crust. And so what we get is, from the principle of isostasy, we get the concept that continents are lighter, thicker, and therefore higher elevation. Therefore have higher surface elevation. Shrink this bugger down. Continents, let's get this to actually move like we want it to. So continents are lighter, thicker, and have higher surface elevation. And your ocean-based sea floor is denser, thinner, and therefore lower lying. And from this, we get the hypothesis that ocean crust, a different process, and continental crust. And we'll be able to test this once we get deeper into plate tectonics. But for now, just save this, and we'll be building upon this throughout the rest of the lecture.